Hi, good evening, Percy, and good evening to all the participants from all over the world. And this is the second day of our. Hi, Percy. I think you can hear me. Percy, you are there. Hopefully, he will join. Yeah.
I'm hearing perfectly.
Yeah. All right. Okay. Thank you. This is the second day of our knowledge sharing workshop on climate change and energy efficiency. I know. We had a nice presentation yesterday on the ocean pollution. So today we are going in a sequence where all the important the points in the country and all over the world, we are going to just touch all these critical points in a critical way with world standard professionals all over the world. So today we are going to talk about a different topic that is on energy and not really energy. Actually, energy is something, but saving energy will be very critical point in these days. Well, if you think about the Sri Lankan situation, we are we are having two parallel bad incidents in the country now. One is the COVID. We are into the third week now for a complete lockdown. So the movements have restricted, and the routine activities have all restricted. So that is one side of the story. The other side, the bad weather. So few weeks throughout the few weeks we are experiencing some sort of a bad weather in the country. With all issues, we got more than 400 viewers today as well. So it's a big achievement in terms of the organizers of the event. So once again, I think it is not the official word of thanks, but I should thank my team who are handling from the University of Maratua. Pasi, recently I saw a nice post in Facebook that was going with your passion and your profession. There were two images. One is the caption was for 50 years, about 50 years, we try to wrap the world with polythene, and finally, after 50 years, the environment started wrapping us with polythene. So exactly that particular statement matching with you. I mean, I know Pasi is a person who who works on waste. So when we say waste is waste, and we don't want to touch the topic, even we don't want to touch waste, and many people even doesn't like to hear the term called waste. But I know many developed countries, waste is money. I mean, you have there are a lot of ways and means of upgrading or improving waste into different steps, and maybe recycling, reuse of the waste, and even upcycling. So Pasi is a person who's more into waste, converting waste into money. But sadly, many developing countries, we still consider waste as a waste. So that is one big issue with developing countries like Sri Lanka, India, and all these South Asian and Asian developing countries. We just consider waste as a waste. But I know developed countries, I'm reiterating the point, developing or developed countries, waste is money. But to tell you, Pasi, very recently, Sri Lankan government, we have taken a sort of a challenging decision, that is to stop 100% these chemical fertilizers and convert our agriculture to biofertilizers. So there we are trying to think of the possible ways and means of converting this waste into fertilizer. At the same time, we are also into this upcycling process, not like all these developed countries like your country and all European countries, but still we are trying to do something. So in that particular small quotation, I like to welcome Percy to this particular workshop on climate change and energy efficiency. But before that, I think we should introduce ourselves and why we are really doing this particular topic. So take 3 minutes, maximum 3 minutes, to understand or identify who we are and why we are really doing this. Yes. There's a small promotional video. We played that yesterday as well. There's a small issue with sharing the screen. I'm very sure that will come very soon. So this particular the workshop is organized by 𝓀, Team 𝓀. Actually, it's a European Union funded project, Erasmus project with 14 universities. So we have 3 universities representing Sri Lanka, and we have some universities in Russia, UK, and some other countries, especially in the South Asian region. We have 𝓀 and Bangladesh there. So that is about the 𝓀, and we mainly focus on climate change and energy efficiency, and we are trying to develop some sort of a MOOC level educational forums or platforms to share the knowledge. It's not really create the knowledge, but sharing the knowledge. I know many people love to create knowledge, but that particular dissemination is not there. So this particular 𝓀 program was introduced to disseminate the knowledge especially on climate change and energy efficiency. Yes, I'll shut my mouth. It's up to you to see what it is.
Thousands of projects are submitted by organizations across Europe in order to receive financial support from the Erasmus program. For this reason, the Commission has set up a transparent evaluation process that aims at providing grants for the best projects. Project 𝓀 is one of the co-funded programs by the Erasmus+. Word 𝓀 stands for Integrating Education with Consumer Behavior Relevant to Energy Efficiency and Climate Change at the universities of Russia, Sri Lanka and Bangladesh. This project, designed after identifying the vital importance of the social and economic development of Russia, Sri Lanka and Bangladesh. These regions distinguish education in engineering and engineering trends. We are a team that represents 14 universities from 7 countries, grouped as 4 program countries and 10 partner countries. We as a team ensure a proper geographical and knowledge balance, also the diversity, because the built environment practices and necessary solutions differ from region to region. The universities of the partner countries are willing to introduce new adapted modes to the different cycles of the built environment and related study programs. All partner universities will participate in the upgrading of BSc, MSc and PhD study programs. The main objective of Project 𝓵 is to upgrade the curricula with 16 new harmonized, multidisciplinary, adaptive MOOC modules on environmental protection technology in Russian, Sri Lankan and Bangladeshi universities. It is to increase their capacity to continually modernize and enhance the quality and relevance of education of students to the global market. Also, the project will spread and promote awareness in the partner countries related to the European Union policies and best practices of energy efficiency and climate change approach towards environmental and energy 2020 targets. Project 𝓵 will consolidate a variety of diverse activities in education quality improvement by delivering extensive distance education programs and a capacity building framework. It will establish an associated network of experts and institutions to continue the knowledge sharing among partner universities.
When we show this particular promotional video and when we were talking about this dissemination and doing all these webinars, some will think we are NGO, we are INGO who just funded by some foreign organization. No, extremely sorry to say and extremely happy to say no, this is all for our personal satisfaction and knowing the duty of the community as a whole. So we thought of doing this particular webinar with just to share the experiences and the knowledge worldwide. I know this even today we have more than 400 participants. If anybody who's missing to join with the Zoom account, you can log to our social media platforms and you can view this video. Unfortunately, not be able to raise any questions, but you'll be able to follow this particular whole thing. Even if you fail to watch the today's program live, you will be able to follow our social media and you will be able to get the video of the previous program. So the yesterday's program is there. And before moving forward, I'll just send you a small reminder. There's a small survey form which was just distributed on, especially on plastic waste and your personal perception. We are trying to collect how you really feel about this particular plastic matter and the plastic waste. So I kind of request you to fill while you are listening to Pasi, and you just try to fill. And also, if possible, if you feel someone will help us on giving the perception, please pass that or share that with your known contacts. So with that, I'm going to Pasi again. Pasi is a real asset. I mean, who can convert waste to energy? You had a nice, beautiful place, Pasi. I know this particular introduction is not enough. We need to have a proper official introduction. So I will ask Gandhi. Yes, Gandhi, it's up to you. You can introduce Pasi.
It is my great pleasure to introduce our distinguished speaker for the day, Dr. Pasi Makkonen. So Dr. Pasi obtained his Doctor of Science in Chemical Technology in 1999. He is the Technical Director for Chemical Processes at 𝓚𝓷𝓸𝓀 in Finland. His illustrious career includes over 30 years of industrial experience in the field of energy production and utilization. From 2016 to 2019, he was the chief engineer involved in the development of the ducted biogas process. In 2015, Dr. Pasi was the responsible consultant for the water quality improvement projects in Finland and Ethiopia. He has conducted lectures on energy efficiency for nearly 20 years. He has been actively engaged in more than 200 international projects spanning over 25 countries, including USA, Germany, Japan, Thailand, and China. He is currently working on biogas production and waste-to-energy projects both in Finland and across the world. His areas of expertise include renewable energy, chemical engineering, and computer science. So over to you, sir.
Thanks, Andy.
Thank you.
Yeah, Pasi, this is not the time to have a discussion or rather ask questions, but I have one single question before you start your presentation. Pasi, in Sri Lanka, we don't have such restrictions. Those who are qualified, those who have the mainly the first class people, they can enter into the university systems as academics, or rather they can become lecturers and professors. I personally working for the industry and working for the university. That's a different story. But in your experience, I know in your country, unless you get a certain amount of experience in the industry, you are not allowed to come and join the university. So I like you commenting on that. I will pass the floor to you. So I really want that particular comment, because this particular audience is more on academics and also the students. So for the academics and also the future academics, I love to hear some comment on that and start your presentation. Pasi, over to you. You can start your presentation. Thanks.
Thank you. So to answer your question, and by the way, good evening to everybody, good afternoon to those who are closer to Finland. It is very common in Finland that the people who take careers in industry do not enter universities as professors. There are exceptions, but usually it goes away that the people who select the academic career stay on the academic career and maybe turn to industry afterwards, but not the other way around. It's possible, but it's not very common.
Thanks, Pasi. You can continue.
Yeah, but there are people who give lectures, like myself, while they are working on industry. So universities, and especially the second grade universities, love people as docents who lectures and courses, because they have the experience to bring the practical issues into the teaching, not only theories. All right, can you hear me well?
Yeah, Pasi. Well,
good.
Nice. I mean,
good.
We can hear you.
Good. So I started when Vasu contacted me what to say and how to sort of emphasize my presentation and speech. And I was wondering whether I could use some old materials I have used earlier for similar lectures. And luckily, I found one presentation, which was a rather long one. And I ended up taking most of the slides from that presentation. So some of the slides are not updated. So some number may be outdated, but not much. And I want to focus on practical perspectives on energy efficiency. So saving energy by not wasting means that every single step that prevents wasting energy should be taken. And to go there, I will show you background, practical examples, and try to summarize with one very interesting calculation we made 14 years ago. But let's go to the topic, which is what is energy efficiency? And I will address energy production, energy transfer and storage, and use of power and heat. And I will stay in thermal processes because hydropower is rather easy, nuclear is more complicated. Same things apply from the primary energy production to the end. But my background is in combustion engineering, and I do believe that there are some issues which are both interesting and unknown to most of the people who are not professionals in this field. So energy efficiency basically needs overall energy optimization. That is the right form of energy production. So we don't select the overly expensive or too low production. We take the right method for power, heat, cold, fuel, whatever we are making. And we transfer the energy, whether it's electricity or heat or cold or fuel, the right way, efficiently, as short distances as possible, which means that we may have to locate the production units very close to the end users. I will come back to that later. If we need to store the energy, we have to have a proper storage, which means big enough, but not too big, and efficient so that we don't lose energy while we store it. Proper use means that we don't do stupid things and waste energy that way. We do the right things. And then finally, use energy properly, not wasting anything when we are using it. Like if you have a stove and you want to cook water, don't turn on the stove before you have the kettle and water in it, because that's wasting energy. Okay. One very, very important concept about energy is that when we have energy, it's the movement of atoms. And this really doesn't tell us much unless we define exergy, which is the workable part of energy. So we may have a huge amount of low quality heat, like hot water, which we cannot use because it has very low exergy. And exergy is the maximum mechanical or equivalent energy that can be extracted from the system when it moves from initial state to equilibrium with the environment, which means from hot to cold. Like steam has a much higher exergy than hot water. Can you see this?
Thanks, Pasi. Yes, we can see you. Thank you.
Okay. Yeah. So if we have a cyclic process where we can circulate energy, the only loss we have is entropy. But if we have irreversible systems where it flows and is kind of wasted, not really, but lost, exergy is lost, then we always have low inefficiency. We cannot avoid that. So all the losses reduce energy efficiency. If we compare energy efficiency to energy saving means that we improve energy efficiency by reducing specific energy consumption. And specific energy means energy we need for heating, production, transport. It's relative per unit of product or specific service. So it's like for ton of product or unit or cubic meter of construction or megawatt hours per cubic meter water heated. So by calculating the specific consumption and then comparing different situations, we can calculate energy efficiency and then start to improve it. Without this kind of concepts, it's very difficult to start doing anything because we don't know what we are doing. So we have to define a baseline and then we compare. Every step in a process, starting from the raw material, fuel or whatever, to the end use, loses something. And in this picture is an example what happens if we have 100 units of fuel. And when we take the fuel, whether it's wood from forests, coal from a mine, or waste from a dump, when we produce the fuel into a form that can be used in energy production, we lose up to 5% of the energy content before it's even burnt or used in an engine. Then we have primary energy production, and in thermal processes, it's very common to lose 10%, just like flue gas losses, radiation losses, etc., unburned carbon, etc. So we have now 86 units left. Then we start to transport it, and we lose up to 3%. And when we are making energy, we normally do make power and sometimes heat. And energy efficiency in power making is usually low. In very good combustion units, big power plants, we can reach 50%. But average is in the range of 25%. And after making this 25%, we transport it, we lose 3%. or heat transport 5%. And in the utilization, we only lose up to 10%, which means that from these 100 units we had in the beginning at the mine, we now have 74 after using it, and we have lost 26. And this is very typical situation. Losses can be even bigger. I audited a couple of small-scale hot water boilers in China, and to my surprise, the situation was such that they were burning low-quality coal with coal carbon content up to 40%, and they were using these rather low-quality chain grade fired units. So they ended up having a fly ash with 60% coal in it, and they were blowing that away. And the average efficiency of the units was also 60%. So they're actually enriching coal in the units, which were supposed to make hot water. Of course, they had some hot water, but the efficiency was really low. And we tried to figure out which are the best ways of improve these units. And the only thing we could have done was to demolish and bring back better combustion units. So every stage we lose something. More stages we have, more we lose. So keeping these chains short, transport distances short, making energy that can easily be used, having high efficiency, and we gain in energy efficiency. If we want to be rude, we can say that very easy way of local energy saving is to press the emergency shutdown button on a power plant. No more fuel is consumed, no more energy is consumed, no energy is produced. But I think the phone will start ringing rather quickly because people are not happy. So in that sense, energy saving versus energy efficiency may be totally different things, but they are size of the same cube or same issue. So be careful when you are using these terms because there is a difference. When I made this presentation the first time, the motivator was EU's energy efficiency statement 2020-2020, which means that there was a goal that energy efficiency should be increased by 20%, renewables should be increased to 20%, and then CO2 emissions should be reduced by 20% by 2020, and up to 30% if there is an international agreement. Countries like Finland have reached target and even gone better than that, but then there are some countries in the EU who haven't. And it's not easy. It definitely is not easy. And the only way to do that is to look at the whole picture. How energy is produced, how it's distributed, how it's used, and how it can be saved, and how energy efficiency can be improved. So if we start to think about energy production, in my opinion, the best way is to be able to select the most suitable fuel. I'm not saying best in the sense of heating value. I'm not saying the best in the sense of environmental efficiency or cleanest fuel, because those are usually very expensive. And in energy efficiency, money always seems to play a major role. So sometimes cheap, low-quality fuel can be very efficient if the utilization technology, the combustion technology is good. And sometimes we just have to go for the best, most expensive, like purified natural gas, like trucks which operate indoors must use that. And of course, the utilization has to be as efficient as possible. So losses minimized. Proper ways of burning, gasifying, making chemical processes, utilizing the side products, etc. In thermal processes, the energy efficiency comes from minimization of losses, because we always do have some things that escape us from at the boiler or plant, like excess air. in combustion, we need a bit more air than the process, the stoichiometric burning needs, just to make sure that the fuel burns properly. The other thing is that if we have a lot of moisture in the waste of wood or fuel or coal, we will increase flue gas losses, because moist flue gas, when it exits the boiler unit, will take out a lot of energy unless it's recovered. Then the equipment condition, preventive maintenance, knowing how the system is behaving and optimizing the process in total is very, very important. There's a nice trick in Finland, like 30 years ago, that when we were burning moist wood, we got a really nice combustion, but we noticed that there is quite a lot of loss in the flue gases because they went out really. If we put a heating unit or cooling unit into the stack and condensate the waters that are in the flue gas, we may make really nice, like 60 degrees C water that is very good for heating purposes, district heating purposes, etc. And we have reheating of the flue gases so that they come out dry and no vapors are visible. Because in combustion and maybe in all chemical processes, there is equilibrium and optimum. If we look at the picture on the left, where we have the flue gas loss, which is higher if we have a lot of unburnt carbon, so we have bad combustion, but it comes also higher if we use too much air. And the optimum is where the fuel is burnt properly and thoroughly, but we use as little air as possible. And if we have this kind of system that's in the right picture, that we condensate the water in the flue gases, take the energy out, then we don't have to worry that much about the excess air loss. So we can put a bit more air to the system without losing too much with the flue gases, and we can move this optimum to ensure a combustion, which means that we can have more difficult fuel or more difficult waste, cheaper fuel, cheaper waste, or even more wet waste to be burned, and still we don't lose. So total optimization, knowing what you can do and utilizing your best policies and technologies is very good in this sense. But as I already mentioned, the most important thing is to keep your equipment in good conditions, because immediately when you start having problems in your equipment, you will have more losses, lower quality process conditions, more emissions, higher fuel consumption, higher burnt carbon, and even more breakdowns and downtime. And a power plant doesn't produce anything when it's shut down for maintenance. So preventive maintenance, intelligent following up systems, and optimization in a production, that helps a lot. And generally, more knowledge you have and more you can calculate by using different measurements, the better situation you have. So production efficiency always can be seen in the profits of the plant. Always. And there's a fine balance between optimizing the maintenance costs versus saving in production. So knowledge is the key. My favorite topic is combustion. So we are talking about a series of exothermic reactions that produce heat. And combustion is the oldest way of making heat. It's not the oldest way of making power, because hydropower has been used for a long time. But making heat for cooking meat, I believe combustion is the first one that has been used. And hydropower is not very good on that. In Finland, when we are talking about primary energy production, combustion, or gasification, of course we do use fossil fuels, coal, some peat, oil, etc. But our emphasis is in wood fuels and other biofuels. So this is just an example to show how in Finland wood is utilized. So we have the growing wood, which we take from the forest. We take it to sawmills, we take it to pulp mills. We produce paper, pulp, planks, wood products, etc. And then we import some round wood, take some byproducts, and then we put these wood fractions into production. And there's always bark, branches, leftovers, sawdust, etc., which can be used for energy. Or in like pulp industry, the lignin in the forest of wood is not suitable for making paper. So it's taken out in a chemical process, and the chemicals are recycled, recovered in a recovery boiler. And when we burn the lignin, we get a lot of energy. So bark, about 50% of a pulp and paper mills energy production, and lignin, black liquor, is another half. So important for Finnish people. And this has led us in Finland to develop very nice combustion technologies, because fossil fuels like coal are usually rather simple and easy and almost homogeneous, so they are easy to burn. And wood is far from easy to burn, I can tell you. If we start with small scale, all kinds of wood burnt stoves can be found in Finland. Open fireplaces, sauna stoves, heating stoves, ovens, etc. Lately, these oil combustion units or burning units for household warming, quite a lot of them have been replaced with pellet or biomass pellet ovens, which can be built so that the feeding system of the fuel is automated. So it's not putting logs into a fireplace. It's a silo filled with dry pellets, homogeneous, uniform, very good fuel, burn really nicely like coal or oil, have like 2% ash, so very little ash. You can run this kind of pellets heat 20 for a month without touching it, and then you fill the silo. So very good way of utilizing biomasses in a small scale and replacing oil-fired units with bio-fired units. But people don't usually make any electricity with the small-scale use. And as mentioned earlier, ecstasy, the value of energy, is the key. So house warming is good, but it doesn't bring us light, or we cannot watch TV or use our laptops with food heat. And in Finland, almost all the units, especially the bigger ones, are combined power and heat units. And in many cases in the winter time, making heat is the key issue, and power comes as a side product, which is interesting because then the production is optimized based on weather, and the power production brings additional benefits. But in these units, we don't need to run for the highest possible power production efficiency. We take a slightly cheaper turbine and produce what we can on the leftover energy, not the other way around. Very typical for these Finnish combined heat and power units is that they are multi-fuel units. They can burn almost anything that has heating value in it. Although the European Waste Incineration Directive made it rather difficult to burn wastes after 2000, but there are quite a few units which still have a very large variety of fuel they can use. I will show an example a bit later. In small scale CHP, we are talking about 500 kilowatts to 5 megawatts electricity, 6 times that as heat. There are some really interesting innovations like this rotary grate, where the fuel is fed into the middle of the fireplace, and the grate is round, so the fuel is spread to all directions. Good thing is that usually the end burning part of the combustion process takes the longest time. This grate has the highest area where it's mostly needed at the last part of combustion. So the first drying and pyrolysis part happens really quickly, and then the secondary burning and final burning, they has more time to occur. So this is a very good efficient unit for small scale combustion. And in small scale, I mean like less than 10 megawatts fuel power. The system consists of fuel silo. This is in Finnish, but I think you get the idea. Where we have the storage, it can be multiple silos that we can feed according to need, different kinds of fuel fractions. Then we have the combustion unit, where the fuel is burned. We produce hot flue gas. Then there's a boiler, which boils hot water. And then some of the flue gases are used to superheat the steam we make. And superheating means that instead of having saturated steam, we put more temperature to the steam to get more efficiency and energy out from the turbine. But there's of course a limit. So there's a curve between pressure of the steam and superheating temperature that must be followed. And turbine manufacturer is usually the person or entity that defines what be and should be done. And in these small scale units, the steam values are rather modest. We are talking about 40 bars, 480 degrees C, especially compared to bigger units. But we have plenty of these small ones in Finland and in the Nordic countries. And they are spreading all over the world as we speak. There are quite a few Finnish manufacturers who have made these. A slightly bigger scale, up to 100 megawatts fuel power, 25 electricity. These fluid aspect boilers have been around from the 60s. And the easiest form is so-called bubbling fluid aspect boiler. The idea is to have fine sand at the bottom of the fireplace, the furnace. And then air is blown through this fine sand so that it starts to move and move so-called bubbling bed. And when it's heated up, fuel is added, the fuel starts to burn and gasify itself inside this bed, which stabilizes combustion. So you'll have like 10 tons of bubbling hot sand. Small variations in the fuel quality or feeding rate do not affect the operation of the boiler. Otherwise, the system is similar, but like the earlier example, it had refractory walls in the furnace. This one always has membrane walls, which means they are steel and water is flowing inside these tubes, and it's a phase flow. So there's gas bubbles, steam bubbles inside the water. We have the steam drum at the highest part of the steam water chain. So it forms a natural circulation. Same phenomenon that we have in the coffee makers, that these bubbles move the water up. And by dimensioning the tubes the right way, we get the optimal amount of steam to water so that the energy is transferred in the walls from the fire and flue gas to the water and the steam. And then we superheat the steam again to make better quality energy. One issue in this scale already is that the flue gas cleaning becomes to be more extensive. There's an electrical precipitator or back filter, sometimes even chemical cleaning, scrubbing systems. And of course, flue gas condensing is possible. Here's an example of a power plant I was making in 90s, 96. The small 𝓚𝓷𝓸𝓀𝓚, 30,000 people, very typical, about 66 megawatts. And already in this scale, we have the multi-fuel possibility. Demolition wood, forest residues. REF means residue extracted fuel, which is basically plastic and paper and waste. And these were burned with very high success rate until this waste incineration directive came to force. And this company had to stop burning the waste because it would have required a really extensive improvement in the flue gas cleaning and measurement systems. And in addition to that, this whole system has to be audited 4 times a year, and each audit costs between 50 to 100,000 euros. So like €500,000 extra operating cost just because of a directive. Then we go the real industrial scale, which can be up to 300 megawatts. And this is the newest, one of the newest bark combustion units at the paper mill. So it is using a lot of bark and wood to make enough steam and power to run 3 paper machines in one mill. So it produces 80 megawatts electricity. And of course, depending on the price and other production rates, it can sell the electricity and buy a cheaper one from Russia if it wants to. But the process heat, 120 megawatts, is needed by the paper making process, which means that this is very big plant. It used to be very typical to use peat, Finnish peat, as a co-fuel, but lately the taxation and decision that peat is not considered to be renewable has almost stopped peat use, which is of course rather bad for the boilers, because peat has some really good benefits in wood combustion or co-fuel as in wood combustion. The ashes and sand in peat help to maintain the boilers clean, prevent corrosion, and even act as a make-up bed material. So less fresh sand is needed to keep the bed in good condition. Then we go to a really large scale. This is a Finnish innovation from the late 70s, or actually early 80s. By increasing the speed of the sand particle, we can make a system where the sand is returned by putting a cyclone after the furnace to return the sand. And the thing is that this high velocity, like 6 meters per second sand, improve the heat transfer from the furnace to the walls and then the steam very much. It keeps the walls really clean. And if the fuel contains contaminants like sulfur, we can put some limestone into the bed material. And this limestone keeps in the circulation until it has heated and becomes so fine that it is blown out with the flue gases and then taken out at a dust collector. So this is a really clever system in all. There are some specific issues which are possible only by using this technology. Like when we are combusting wastes and start having problems with corrosion and fouling in the flue gas channel where the superheaters and extra heat pipes are, we can locate some of the heating surfaces. On the left part, you can see the nomination loop seal. If we put tubes inside the sand bed in the loop seal, we can have a very high efficiency superheating, which keeps itself clean and corrosion free. And there are a couple of companies who have used that in their products. And nowadays, every single circulating fluid aspect boiler is equipped with this kind of system. Here's an example of, at the time, largest biomass combusting circulating fluid aspect unit, 550 megawatts, which is like utility size coal combustion plant. And this is a paper mill, pulp and paper mill power production unit. In this case, the quantity of different fuels listed was 13 to 15 different ones. So that's a lot of variety. And to tell about this scale of operation, if the unit was run only on forest residue, a truck would be unloading every 8 minutes to provide fuel for the unit. So it's huge. And here you can see that we do know what we are talking about. The red dots are the CHP units using domestic biofuels in Finland. And there are quite a few ones that have been built lately and being built. So we do what combined heat and power is. And that's why there are so many Finnish, and have been so many Finnish boiler makers who are doing good business in the world. And Valmet is nowadays one of the leading manufacturers in the world on these technologies. I mentioned black liquor. Why? Because about 50% of the energy produced in Finnish pulp and paper industry is coming from lignin in the wood, which is black liquor. So the main need for black liquor is recovery of pulp chemicals, and the energy production is of the secondary purpose and task. But when the heat recovery is there, of course the heat is used, and modern soda or recovery boilers are really huge. They are in the same scale as this big biomass combustion unit I showed. So they are big and efficient, very, very efficient. Okay, then we step a bit deeper into the deep end in chemistry, because combustion is rather simple. You have a fuel, you have air, you have heat, you have chain reaction, and then you have energy. Gasification aims for converting solid or liquid fuel into gas, which can then be used as a fuel in many cases, but it can also be a syngas, which is used as a chemical in many processes. And when we have dry material, whether it's cellulose, lignin, hemicellulose, which has some moisture, to gasify it, we need heat or energy in one form or the other, but heat is the easiest. So we burn small part of the fuel, and with this heat, we dry the material. We have a step called pyrolysis, where solid material turns into liquid, and then in gasification, solid and liquid material turn into gas, which contains CO, hydrogen, methane, CO2. And when we are using air, it also contains nitrogen, but it doesn't contain any O2, because this O2 would react immediately with hydrogen, so it's O2 free. And the heating value of this gas can be between 6 to 30 megajoules per cubic meter, depending on how we gasify and what we do. We can have multiple ways of building the gasifier, as long as we remember that we need the heat from somewhere, and we need this oxidization part in the process that provides the heat. But then when we oxidize the fuel, making hot flue gas, if we direct this hot flue gas through a bed of material that has organic substances, the heat will gasify the rest of the fuel. So we have co-current, mixed current, counter current, fluidized bed gasifiers, etc. Gasification has, as I mentioned already, plenty of uses. And in '96, when Finland came up with an idea that why not use a gasifier as a fuel cleaning system, which means that at the Lahti project, the client had a coal and natural gas combustion unit, very high efficiency, nice power plant. And they wanted to start burning biomasses and some waste into that furnace. But it's very difficult to grind biomasses or waste so that they can be burned in a pulverized coal unit. And the idea was that instead of trying that, we built a gasifier where we turn this fuel into gas and then burn that gas in an existing unit by replacing one of the burners. And what happened was that this gas replacement reduced the sulfur emissions by 30%, nitrous oxide emissions more than 20%, and replaced about 1/5 of the coal and natural gas. And we tried the gasifier with used tires, it worked perfectly, wastes, and so forth. But then 2000, when this waste incineration directive came, the system was shut down. But the good thing was that Lahti made a complaint, and in the modern version of the waste incineration directive, if fuel is gasified and gets cleaned, the waste incineration directive doesn't apply to that power plant. So we can have a gasifier which is used as a fuel cleaning unit, and then we can have an existing energy production unit where we burn the gas. Money saving, energy efficient, doing things. And then, of course, if we think about a bit more scientific and fine ways of utilizing the gasifying gas, if we reform it and use the hydrogen, we can run a fuel cell with the gasifier gas, syngas. Of course, in this case, if we want to be efficient, we need to use the rest of the gas somehow. Usually we burn it because it contains CO and methane. But if we have low nitrogen gas, which we use like oxygen, distilled oxygen, if we use that for the gasification, we get a lot of hydrogen in the gas. And then the rest of the materials are very easy to separate from hydrogen, and then can be used in a fuel cell. Or if we are talking about CO2 emission reduction, this is a real example of a Polish big coal combustion unit, which had the opportunity to use 20% of biomasses on side of coal. And the size was fuel power 1 gigawatt, so 1000 megawatts. And it was producing 460 megawatts of electricity. Real utility size, big boiler. By replacing some of the coal with biomass and by increasing the production efficiency from 40 to 45, we could reduce the CO2, specific CO2 emission a lot, like from 900 to less than 600. And it doesn't really cost that much extra because biofuels are still rather inexpensive. The unit is capable of doing it without losing anything really. And when the efficiency is high, the power production is very profitable. Of course, we could go further, like making this 40% reduction of CO2 specific emissions by increasing the efficiency, replacing some of the fossil fuels. We could go for the CCS track, carbon capture and sequestration. But this is something that is expensive. And the only way right now to make it feasible is to bind the CO2 into minerals, because then it stays there. CO2 content is too low so that the gases should be liquefied, and usually there has to be some use for the liquid CO2. So if it's used as a chemical, it's again released and it's zero-sum game. But this is example from Norway. And this is actually being used and tested, that when oil and natural gas is drilled, the gas is treated, oils are treated, some of the fuels are burned for energy. CO2 is taken from the flue gases and then pumped in the oil and gas wells where it stays because of the pressure. And by doing that, more oil and gas can be taken out from the ground. So this extra oil and gas pays for the reduction of CO2 with carbon sequestration. And it's not poor boys game, it's expensive, but it's being done, and in some places it brings profits. It has nothing to do with energy efficiency itself, but it has to do with material efficiency and environmental protection. So sometimes low energy efficiency is accepted because the other targets are so important. When we have the energy in our hands, we need to transport it somehow. So when we are talking about heat and power co-production, we usually have the basic heat load, whether it's district heating or a process, and then the electricity is made as a side product. Fortunately, in Finland, we have really 4 seasons, so that we need the heat 3/4 of the year. Like summertime is the only thing area or time of the year that we only make hot water for showers and other purposes with district heating heat. Otherwise, we heat up the buildings. But then again, Finnish summers are becoming warmer and warmer. So we also need ways to cool down the houses and offices. And we have come up with an idea of district cooling. So by building district heating nets, we can also build district cooling nets. And then electricity transport is that we have a modern net, but we have relatively long distances. So the CHP units in Finland are really often built very close to urban areas, so that the transmission distances are short. The heat is next door, I would say, and the losses are minimized by doing that. And of course, when the central heating unit, the CHP unit, is close, it can really quickly and easily regulate its operation based on the need. So these are not fixed load units, they operate according to the weather. District heating is a $1 billion business in Finland. So we are talking about huge sums of money. There are a lot of companies. Almost every town has its own company, although there have been mergers and purchases, so that some bigger players like Fortum are running quite a few of these district heating boilers. It's cheap compared to anything else. I mean, if you have your own forest and burn wood in your stoves, then you may end up having cheaper heating system, district heating. And we sometimes mockingly said district heating is heat loss heating, so that if a power plant or pulp and paper mill makes power for its own needs and heat comes as a side product, it's waste heat, so we use this heat to heat our houses. And almost half of Finns live in houses with district heating. So it's about 50% of all the energy heating in Finland is district heating, or sold as district heating. And oil burning is being reduced greatly. We have really good governmental substitutes, like 4,000 euros direct money if one gets rid of oil and replaces it with district heating or heat pump or something else. Here you can see the yearly distribution of utilization of heat. So only during the warm summer days, district heating is used for making hot water for different purposes. The rest of the year, it's used for heating houses. So why district cooling? Every office could build or put its own air heat pump, like most of the countries are doing. But when the distances are relatively short, we don't have that big cities in Finland. Helsinki is the only one, together with Espoo and Vantaa, that goes over 1 million people. So they are in areas, small cities. The energy production is close by, and the knowledge how to build these district heating networks is there. So by putting a new tube for district heating, the same dig can be used to put the cooling pipes. And you basically don't need that much building area to be cool, to make it profitable. So like Helsinki offices, most of the in the center are now under district cooling instead of localized cooling systems. And chilled water is used, and then there's a local HVAC system which cools down the air which circulates in the building. So it's very nice way of cooling, and it feels like the central air conditioning in your car, that you get fresh, nice cold air into your office or house. Cooling can be made from seawater, lake water, groundwater, or you can even convert heat to cold by absorption heat pumps. And in Turku, in Finland, there's a company that is doing exactly that. So excess heat is converted to cold because in the summertime, it's more profitable to run the power plants, make electricity, and then use the heat to make cold. The unit efficiency is not very high, but it's still very profitable because it has a very nice value, and this can be really, really interesting because compared to these air heat pumps, the efficiency is good. And it really depends on how the system is built, but usually there is 1 or 2 local house converters that take the cold from main line and then distribute it by air system or by having these room-based cooling systems, because you want to have the cooling at the top of the room because cold goes down and warm air goes up to make pleasant and efficient put it up. There's a map of Helsinki, and there are several independent district cooling nets, and more are being built. So this is the old picture, but gives you an idea. And other companies and other towns like Tampere are right now building cooling networks. The power things are not that great yet, but they are being expanded. And this is something that Finnish companies could export to other countries when the time is right. Then when we go to power transmission, which electricity, taking electricity from one place to another, power lines usually use the alternating current which comes from the generators because of their operating principle, and they don't do anything more than maybe increase the voltage. So the frequency is in 50 to 60 hertz. The voltages are up to 100 kilovolts, rather high in high voltage. Medium voltage can be 10 or higher, and low voltage is the local, like 400, 350. This alternating current networks is coming from the States from the 1900s, 19th century, where Edison developed the DC distribution network, but lost to Westinghouse's AC networks. But then again, modern power electronics, like frequency converters and stuff like that, have made it possible to build and reintroduce direct current distribution, high voltage DC. So the reason why we have this high, up to 400 kilovolt voltage in the electricity distribution network is that the higher the voltage losses we have, as a Faraday's law and so forth, no problem. So we have the main grid 400 kilowatts, local mid grid 100 kilovolts, and then turning those local into 20 kilovolts, and then we have these local transformers making this lower voltage electricity, which is then used directly in the houses. And in Finland, the distribution losses, despite the long distance, are only 3.5% on the average. In Lapland, where the distances are really long, we have higher, and in the south, where we have a lot of production units almost next to each other, the losses are lower. The district or direct current is an interesting technology because it has lower losses. There's no cosine phi loss, phase loss. It's good on that. And if the electricity is used in anything else but in rotary motors, by having it direct current can reduce the need for transformation and voltage lowering losses. So it's basically an inexpensive solution, but to be competitive with AC transmission it has to be a long distance transport. And in Finland, we only have one DC transport line between mainland and Åland. the island between Finland and Sweden. Okay, back to gasification. It's not only energy production that can benefit from this technology. Almost anything that has carbon chains in it can be gasified, turned into gas, and then this syngas can be cleaned from CO2, and the rest can be converted to diesel, Fischer-Tropsch diesel, methane, dimethyl ether, or hydrogen for fuel cells. So by developing high-efficiency gasifiers, we have a multi-variety of raw materials which we can turn into almost anything we can imagine. And an example of how it's being used in big scale in Finland, a town called 𝓚𝓷𝓸𝓀𝓏𝓭𝓰 has a big pulp and paper mill, and they are making a lot of biodiesel by using the energy excess produced by the pulp and paper mill. And then they use this to gasify, treat the gas, make syngas, and turn it to wood diesel. And the good thing is that in this synthesis, side gases are reduced or released. And these are then again burned in the power plant to process steam and power. So we can easily turn wood-based fuels, straws, etc., into liquid fuels for transport purposes. And the scale is huge. I think it was like 400 million euros as investment, but nowadays smaller biodiesel plants are being built as we speak. So this is the emerging technology. And again, Finland has a lot of experience on this, and we can export our knowledge on this. Then we store the energy. Chemical energy is easy. We need a fuel tank, and that's it basically. Small scale heat storage. We heat up an oven, it stays warm. We heat a fireplace, it stays warm. Keeps the house warm for 1 or 2 days. Very easy. Baking oven, very good. Quite a lot of Finnish detached houses have these baking ovens, wood fired. They are large scale thermal batteries. I will tell a bit more of that later. But electricity is difficult to store, like chemical storage, batteries, or kinetic energy hydropower flywheels, or supercapacitors. Why this technology has been innovated and built is that it's beneficial for the CHP plant to run a stable load. Every variation in the load reduces overall efficiency and puts stresses to the equipment. If we have a water tank where we put hot water when we are not needing the heat in the source or heat streamers, we can fill the accumulator up, and then when like people wake up, have morning showers, etc., we get the heat from this heat accumulator, and the CHP plant keeps on running steadily. It doesn't even see the change in the heat consumer's behavior. On the right hand side up is a very big power plant in Denmark, 𝓚𝓷𝓸𝓀𝓏𝓭𝓰, and those tanks in front are heat accumulator tanks. So Denmark has district heating. And in China, it's been introduced. Beijing has a couple of plants and so forth. So it's a very good innovation and simple as because it's a water tank. Then storing electricity. Ghema made a very nice presentation in the early 2000s about the scale and usability of electricity storage units. So pumped hydro can be built into huge scale, and like in Oslo or Norway, they are using these water reservoirs. They are filling them up when the power is cheap, and then selling it out when it's needed and sold abroad and get a lot of money on that. High energy flywheels, small scale, but bring the power quickly. Power quality at ups, UPS systems, uninterrupted power systems. They are quick and can be built to big ones. But I have circulated energy management because if we know the local system thoroughly, by energy management, production management, transport management, utilization management, we can have a really, really nice effect on the power consumption and production, and we can call this storage. So if we have a good energy management system, we don't need as much storage. That's why it's so important. It is part of energy efficiency. Cost. The arrows show where we should go. Capital cost low, operating cost low. Lithium-ion batteries are very good, but they are expensive. The prices are coming down, but they are still really expensive. If one wants to build household size lithium-ion battery storage for like 10 kilos, the cost in Finland is like 40,000 euros. It's the same amount of money as Tesla's battery pack. So that's very expensive. But then again, if you want to build same size of pumped hydro, you don't get the permits because you need a big pool and generator. So it's the same price. One of the most important parts of the whole energy efficiency chain is the use. So depending on the use, whether it's household, chemical process, industrial process, manufacturing process, vehicles or whatever, everything starts with planning. In buildings, it's insulation and heat and AC technologies, heat and AC. For example, in many warm countries, insulation is not considered good because there's no need for keeping heat in because there's enough heat out. But it would be good to keep the cold in because there's a lot of electricity needed to make the cold with the AC unit. And then you lose the cold immediately due to lack of insulation. You're just losing it. You're throwing away money and heat. Traffic planning, urban design, very, very important. I mean, if you make a mess so that cars stand in rushes and queues, you lose all the time energy in fuel, make people frustrated and unhappy. Process design, of course, in all kinds of manufacturing processes, material choices, and so on. And many of these are user choices. So to optimize the whole thing, you need to keep in mind material efficiency because making materials consumes energy. And if you have material that cannot be recycled in any way, not even as energy, like asbestos, then you are lost because you put a lot of effort to making the material, you use it for a while, and then you just have to throw it away because it becomes hazardous and difficult waste. And then when we go to the whole picture, what we have as raw material or primary source of energy, how we use it or convert it to something, what we have in the meantime, whether it's power, heat, liquid fuel, solid fuel, whatever, then how we utilize it and which kind of system we have to utilize it. If you want to optimize this kind of chain, you have to know the contents of everything in detail, costs, technologies, processes, chemistry, physics, you name it, IT. And this is something interesting for universities because self-learning systems, neural networks, etc., would be a really good tool for this kind of optimization. And there are very few companies who right now do this because they just don't have the knowledge how. They need to learn from academia, and academia needs to do the dirty work to make these systems and optimization algorithms and so forth for the companies to use. I promised in the beginning of my presentation that this is rather interesting and describing example how situation today is and how it could be. This is a real example from China that a household or block of flats for some 200 to 300 people needs for making of electricity 4 tons of coal, which means 7 tons of our CO2. And for the heating in northern China, 20 tons per hour of coal. This is the low efficiency unit I mentioned earlier, which is 36 tons per hour CO2. So 24 tons of our coal used and producing 43 tons per hour CO2. When it could be done so that the whole system, the houses are optimized, wood is used in a good GSP, the demand would be 4 tons per hour with zero CO2 emission, and 5,000 megawatt hours extra electricity here would be produced. This is a huge difference. And just because the efficiency in the production, transmission, and utilization is very low, by improving that, we could go to a really nice situation for economics, environment, and efficiency. So basically, when we are talking about energy saving, we should start from the end use, and energy efficiency is the whole chain. Every single piece in the chain needs to be evaluated. And then we need to think how and why we are doing the things we do, because we don't want to end up in this, that we do stupid things because we don't understand anymore why we are using lamps. This Mr. Rinkola used to be a very famous Finnish green person, a fisherman who was against all kinds of technical improvements in household living. So this is his lamp, and I would prefer the LED lamps nowadays. So thank you, and I think I have a time for discussion and questions, but I thank you for your interest in this lecture.
Thanks, Pasi. It was a very interesting presentation. Energy saving start with the end use. That is what all of us says. But you tried and you managed to prove that it is not the real case. You have to start from the start of the process, the transmission, and then the end use. So I mean, any person to keep the same audience 1 hour or rather 1.5 hours is a real big challenge. I think, Pasi, you managed to do it. We have the same set of audience who were there at the beginning, even though one or few people left the presentation halfway. Still, we have the bulk. So I think it's a plus point from your end and also from our end as well. But Pasi, now the biggest challenge that is to continue this particular Q&A session. Just to tell you about the Sri Lankan scenario about with respect to the energy, our total the total capacity is slightly above 4,000 megawatts, but the daily peak is slightly about 2,500. Nowadays, it definitely should be less than 2,000 because of this particular lockdown. Even within that particular 2,000 megawatts, the bulk goes to the domestic sector. So that is one of the biggest issue in the country, because we that proves that we are not really geared into production or production-based economy. So that is something we have to look after in the future. So in your presentation, that was I picked two interesting. I mean, there were a lot of, but very interesting 2 points. One is about this domestic level. What is that biomass? Small unit. So that was very fascinated in Finland. So thanks to share that particular experience. The other one is your district cooling system. As far as I know, that's a patented product, Pasi.
Yeah, there are companies who have patents on that and proprietary technology. So in principle, it's very easy. But when you make it in practical terms as efficient as possible, then you have to know quite a few things. And especially in Finnish conditions where the winters can be minus 30 degrees C, if you build it the wrong way, you will break the tubes, definitely.
What do you think about the Sri Lankan scenario? I mean, not about the cooling, but okay, we'll take cooling. We are a tropical climatic country where the temperatures and the humidities are really high. What do you think? I mean, can we share the same the experiences you are enjoying in Finland, or you recommend something else as Sri Lankans?
It really depends on how much do you get new construction, because if you start to dig up an old city, it can be really difficult to make a new system, whether it's district heating or cooling. But anytime you build a new area, you should consider putting the piping into the ground, because you make the sewers anyway, you put the electricity piping there, you put the IT piping, telephone cables, etc. It's not a big cost to put a couple of more kilometers of pipe, even if you don't use it, but it's there. And when you have the chance, then you can take this district cooling system into operation very quickly. I mean, absorption heat pumps, if you have a source of cold water somewhere or well you can dig, it's rather easy, and the technologies have evolved so much that the pricing is really promising right now. Like we have a big house, 360 square meters, and we are using oil for now for heating, and we are converting that late this summer into ground heat, and we are considering using some of this system for cooling as well, because we have in summertime big rooms which end up getting rather warm because of sunlight. So it can be built at small scale, and the pricing of the heat pumps has been really interesting because they have gone down a lot lately. And even the big ones needed for district cooling systems, they are not that expensive anymore.
Okay. These are all my personal questions. Pasi, you talked about this biomass, or rather biofuel. I mean, burning wood. Well, many people. I mean, I'm not really claiming who are going to talk about this particular topic, but anyway, many people claim that biofuel is not a sustainable or a eco-friendly or an environment-friendly solution, because when we burn it, you emit a lot of carbon dioxide. At the same time, you cut the trees, and that is the sink of carbon sinks available, natural carbon sinks, and you cut them and you add the carbon dioxide to the atmosphere. So as an environment sort of a person who has more concern on the environment and the environment conservation, what kind of comment you, I mean, it's rather a comment I'm really requesting from you, how you tackle this particular matter?
Basically, this is politics, fully politics, because if we consider wood, forest wood, it grows 50 years, and when we burn it, we release the CO2 or carbon it has gotten into it during this 50 years. But in next 50 years, it grows back and captures the same amount we released. If we have fast-growing crops like grass, every year they grow, we burn them and release the CO2, and the carbon is captured again for the next year. So short circulation crops have really, really low CO2 emission in real life. It's basically the harvesting, transport, and losses that is causing the real CO2, not burning biomass itself. But of course, if we, like Swedes, consider peat as a slowly regenerating biofuel, it takes 1,000 years, but it still grows back. And nowadays, this is considered to be too long time, so it's fossil fuel, we cannot use it. But in my opinion, it's still renewable, but slowly renewable. But grasses and the stuff you have there, because you have more warmth and moist and so forth, you can grow things that grow really fast and have a short circulation CO2 capture and release. The other issue is that nowadays people are talking about making biochar and keeping that as biochar, not releasing the CO2, because it's not burned, it's just taken from the forest or growth and stored somewhere, and that's it. And the good thing is that if you have a swamp, it produces methane, which is very intensive greenhouse gas compared to CO2. If you reduce the production of methane, then you save the planet. So it's not simple, but in my opinion, quickly growing biomasses are always CO2 neutral, and wood and trees are renewables, but they take a bit longer time to renew. But they capture the same amount of CO2 we release when we burn them.
Thank you. I know it's really political, and I wanted to add one person another view to this particular political debate. So with that, let me move to the questions raised by the attendees. We have a full list of questions. I'll not be able to answer all the questions as we are running out of the time. But anyway, the one from the Sri Lankan construction industry, who is involved with the construction industry, he asked, what would what are the ways and means of do energy efficiency related building construction, especially the building construction industry? What are the ways and means available to have an energy efficiency system in building construction industry? Can you give a quick response, because I think otherwise it's not. we are not
it's
doing
with design,
justice.
design, and then second is materials. By doing the design properly, it's not only how the building is constructed in the architectural terms, but where it's located, if it's shaded by trees and stuff like that. So everything that is related to building and surroundings must be designed properly, and then materials selected so that it can be built safely, efficiently, and not to lose all the cold or heat that is put into the system, into the building.
In very simple terms, what you say is not the initial cost, but you think about the running and the operational cost. Yeah.
If you do the design properly, you will lower all the costs, building cost, operating cost, everything. If you do it badly, you will lose a lot.
What do you think about the building BMS, building monitoring management systems? You recommend them?
I love those. I love those because, as I mentioned, more knowledge you have, the better you are off, and you have basis for decision making. If you have measurements and information, if you are guessing, it's very probable that you will end up doing wrong things or right things at the wrong time. And
well, go ahead, Pasi. Well, there's another. I think he wants to know the price of your domestic biomass that unit. What will be roughly the cost of that particular unit in Finland?
Wood-based fuels are 20 euros per megawatt hour as we speak. That's a long-term contracting. And then it might be possible to get a bit cheaper if your unit is capable of handling a bit more moist woods, because it's always based on heating value, not tons or cubic meters. Peat is 22 or something like that. Natural gas, you have the pipeline is 25 and so forth. So relatively inexpensive, but still it's a cost. Okay,
thank you. There's another interesting question from a Russian student. I'm going to read his whole question. It's with a small preamble given. I'm a student from Russia. Recently in my hometown, with a population of 190,000 people, the student conducted a survey. The question was one question they have asked in the question, the survey. If you are provided with all the necessary infrastructure to dispose the lithium batteries, will you dispose of them correctly? So that was the question asked by these students from this hometown, and only 5%, only 0.5, should be 5%. 5% of the population answered yes. All the other 95%, they say no. So that is the attitude of the community. So we talked about this community and we are trying to convert them on energy saving. What do you comment on this, Pasi? I mean, how much we say, whatever the knowledge we shared, but if you can't change the attitudes of the people, nothing is immaterial. What is your comment?
In Finland, we are using quite a lot of PET bottles and also tin cans, aluminum cans, and we have a recycling deposit system. So when you buy a beverage, a soda, you pay 15 cents as a deposit for the can, which you get back when you return it. So same thing could be used for batteries, so that you pay a deposit and when you return it, you get it back. People would love that because then they will bring the batteries back. Everything will be brought back in that because it's worth money. If it's not worth money, then it's thrown away. Did you get my meaning?
Yeah, I think Dr. Pasi, I think there is a technical difficulty
I may also.
Yes, we got your answer.
Also suffer from flat battery on my laptop soon, so I still have some 15 minutes hopefully left, but this is a new laptop, so I'm not sure how accurate it is.
Thanks, Percy. We are talking about power, saving power, but unfortunately, because of the bad weather, I lost power. Anyway, I'm really dark environment, so I'm not going to open my video on. So we will try to quickly go through the questions raised by them. Another interesting question. I'm really picking a few questions from the audience. Otherwise, we are not really doing it justice. This lady, she's from India, and she say, actually, the question is, can we comment on can we comment on future biomass conversions? So that is the question from this lady, and she's another question. I will couple that with this. She's a teacher from India, and she wants to know what are the tips which we can pass to the students on energy conservation. Percy, over to you. I think we have a big issue with the connection. We lost Percy as well. I don't know what exactly happened with the connectivity. He was talking about losing his power because he was a power concerned person. So he came out of his house, and he wants to be in the natural environment to do this particular webinar with us. But anyway, I think he lost his power. We lost power. I'm not in. I can't really even switch on my video because I'm in a thick. I'm in dark because we lost power in 𝓚𝓷𝓸𝓀𝓵 area. But anyway, we will see whether he will be whether he will be able to join the webinar again. If not, with his absence,
sir, I think Pasi just called me, and he said he will come back with his phone.
Right. Okay. That's great. That's great. So he's going to join.
Yeah.
So if you have, this we will give him 1 or 2 minutes. I mean, these are always very common when we are doing online webinars. I mean, whenever we are depending on the technology. So if there's an issue with the technology, we will lose. If it is a face-to-face, I mean, whatever happens, we at least can see the people face-to-face, and we'll be able to have a live discussion. But unfortunately, due to COVID, we'll not be able to have that sort of discussions. But I personally love to. I mean, I was not really happy with these online education and online webinars in this nature. But when we started this particular webinar, I think this is really valid because we'll be able to connect a lot of people all over the world, and whenever they want, they feel. I mean, they don't have to worry about the time differences. No other matter. They can just join and share the experience. So that in that particular context, the webinars and these online forums are really important, and also the audience. And we have, I mean, if you do it, well, it was a coincidence. Percy came from his end, and I got the power as well. So if you do this particular thing face to face, we'll not be able to get more than 50, 60 people listening this particular webinar. So that is another good experience for us with these online webinars. Percy, thanks for coming. I mean, you not like you are not a talker. You with your actions you prove that you are into energy saving. You're not inside, you're outside with the natural light and the natural environment. Thanks for joining again. Percy, I was asking you about this Indian teacher, and she wants to know at least 1 or 2 tips to share with her students on energy saving. Yes, over to you, Percy. Percy, your mic is off. Percy, your mic is off.
Okay, now it should be on.
Yes. Now it's
quickly showing the environment. I mean, this is the Lake Saimaa.
That's super. Wow.
Yeah, I'm living in a country house, and our internet there is rather bad, so I had to come to the
So
small
it's
village.
a nice experience for us as well. I mean, a person who's coming with the natural environment just to see the surrounding. It's not in a closed environment, closed cell. So thank you very much for showing your the outer setup. Thanks, Pasi. Go ahead.
Yeah. So energy saving and energy efficiency, it usually comes from small things like everyday life. You need to consider when you have to travel, you have to think how you travel, whether you go by foot, by bike, if you have to take a longer distance, or travel by car. Then there's always a choice that if you're using public transport, if it's possible, because that's usually more energy efficient than having your private car. And when you have your private car, then you have to consider which is the shortest route, quickest route. And of course, selection of the car is important, whether you can afford an electric vehicle or low consumption gasoline, high mileage car. Like I have a hybrid diesel, which has a very low consumption, high mileage, and so forth. So small things. And like in buildings, everything comes from design. Here, everything comes from these small thoughts. But if you think what you are doing and consider options and select the best option every time, you are efficient, also energy efficient, and saving energy, among other things, because material efficiency is energy efficient as well. So if you buy a product, check if there's an alternative, how it's packed, and so forth. All the small things matter.
Thanks. Well, that is again one wanted to know Finland experience about this e-waste. The question is, how do you utilize e-waste for energy saving? What do you think, Pasi, with your Finland experience?
We have some specific companies. This 𝓷𝓸𝓸𝓀 power plant I showed, which is the community CHP, it's next to an industrial zone where companies, like 10 different companies, have specialized in recycling of different materials. There used to be a company that was collecting only used TV monitors, vacuum tube monitors, but of course they are not available anymore, so it went bankrupt. But there's an e-waste company that is melting the composite socket boards and electronics into materials. They are recycling a lot of different steels, copper, even gold. And when they are doing that, they are using the plastics for energy. So they are efficient in that. But the small problem in Helsinki area is that they built a big waste combustion unit at Vantaa to handle the mixed wastes. And by building that, they run a couple of these recycling companies into bankruptcy because nobody wanted to pay the money for recycling. They just threw this electric waste into the garbage, which was bad. And there has been a lot of debates about these mass burning units, as they are called, where you can put anything in and it burns and brings some energy and heat. I don't like those. I like recycling. I like these multi-fuel units, which then can handle sorted waste. But this kind of e-waste must not be thrown into these molochs. It has to be recycled one way or the other. And luckily, we do have companies in Finland who have specialized in this. There's also a company that is making big profits by recycling different types of batteries. And they sell a lot of recycled metals and make a big money on that.
Okay.
But it's specialized industry, so it requires quite a lot of knowledge and also some nerve to start that kind of company, because it's not really a gold mine, but it could be a good business.
But this is never ending. There are a lot of questions coming from different regions of the world. But we will take one or two and we will wind up the thing. Otherwise, you will stuck with your time. when you think about the nuclear energy, Percy, that was the big bus in energy generation. What do you think about the future of nuclear power generation in the world? Will it be there or will it die down naturally?
This is a very good question, because Finland is now starting its fifth nuclear power plant, which is delayed almost 10 years because of all kinds of issues. But at the meantime, quite a few institutes in Europe are studying the small-scale nuclear units, whether it's heat production or power and heat production. And it might be that these small-scale reactors are a step towards fusion technology, because these new approaches and tests proven that plasma can be contained and maintained, may lead up to a fusion nuclear power system in 10 years. And in the meantime, these small-scale units may clear the way for such reactors. But this traditional old-fashioned nuclear power production, that will fade out, although China is investing a lot in nuclear power. But in China, they have a couple of really interesting new ideas, like this South African ball bed reactor, where 10-centimeter diameter or 6-centimeter diameter uranium oxide graphite balls are in a pile, and then it's cooled with gaseous helium, and this helium is then bringing the heat to the heat exchanger. And if something goes wrong, you just spread the pile and the nuclear reaction stops. So this kind of development may bring us new ways of producing nuclear power, but these old fission Russian nuclear reactors, they will fade away.
Thanks. This is my last question. With this, I'm going to release you. This is a very big burning issue in the country. Pasi, about these EV vehicles, you were talking about these electric cars in your country as well. In Sri Lanka, not recently, but 2-3 years ago, we imposed a new law saying EV, the batteries are hazardous waste. So there's a huge tax on EV batteries, and with that, the EV market has gone down in a drastic way. So what do you think about these the recycling of these EV batteries? So that is my last question. With that, I'm going to release you.
If somebody comes up with a good idea how to do it, it would be perfect. But right now they are difficult waste, really difficult waste. And there have been lately some discussion about new findings of new types of batteries which use less harmful materials. But until those are commercially available, we have to stick on lithium-ion batteries and, of course, sulfur-lead batteries, which are the traditional way of making batteries. So new innovations in recycling are needed. I have this hybrid, small 8 kWh lithium-ion battery, and this car is 8 years old, and it's lost 1/3 of the capacity already. So in 5 years' time, I believe that the battery needs to be replaced, and I have no idea what is going to happen with the used battery. So yeah, hopefully somebody comes up with something. Yeah.
How much we say EV is going to save the environment, in another way, we dump them all back to the nature.
Yeah.
Well, thanks, thanks, Pasi. I think you enjoyed the 2-hour session with us, because you managed to keep 500 people with you throughout, from the start to the end. So congratulations from our end. Pasi, thank you very much
for inviting me on this.
Yeah. Keep in touch, Pasi. I mean, there are a lot we'll be able to do together. So once again, thank you very much. And tomorrow's presentation. Yes, tomorrow's presentation will be another interesting one. Will be done by Nina, and she's going to talk about this urban landscape and how that is going to affect the climate change. And she's going to share some world experience and also the Russian experience. So keep in touch. So the tomorrow's presentation will be much more, very much interesting, like Pasi's presentation today. So we are about to wind up the second day, and once again, thank you very much for coming. You let us be strong and continue this particular discussion for all these 6 days. So once again, thank you very much, and I hope all of you will join with tomorrow's presentation as well. And while inviting all of you to attend tomorrow's presentation, I wish to thank Pasi for giving the support and the encouragement from Finland, and thanks to all the attendees. So see you tomorrow. Good night.
Thank you. Good night. Bye.
Okay. Bye.